All right, these ones here. We had 4 steps. The 4th step you're not getting any marks for, so you don't, and you won't lose marks even in your HSC if you don't write it. But step 1, let's start with that. And the acronym was TAP. If you guys remember this, test, assume, assume. It's harder to write this way than I thought. And then prove. Okay, test, assume, prove. So step 1, test true for n equals the very first case, which is n equals 2. So your left-hand side equals 12 squared, which is 144. Your right-hand side becomes 7 squared plus 5 squared. 7 squared plus 5 squared is 74. And of course, from that, you can say left-hand side is bigger than right-hand side. Yeah, 144 is clearly bigger than 74. All right, all good? Step 2. Step 2 was assume true for n equals k. So that one we wrote 12 to the k is greater than 7 to the k plus 5 to the k, and that's it. And then step 3, and you have to bring your assumption in. Don't forget that. Step 3 is prove true for n equals k plus 1. So in other words, you're trying to prove that 12 to the k plus 1 is bigger than 7 to the k plus 1 plus 5 to the k plus 1. Right? 7 to the k plus 1 plus 5 to the k plus 1. Okay, all good? We start off with our left-hand side, which is 12 to the k plus 1. Right? Anyone know what my next line would be? Don't forget, I need to bring in my assumption. Azra, you might know it, because you just worked on this.
Would it be 12 to k times 12?
Yeah, exactly right. So 12 to the k plus 1, you're going to use your index laws, break that up into 12 to the k times 12, because then you can actually start bringing in your assumption. Right? Otherwise, you can't bring it in at this stage. So next line is 12. Sorry, no, next line. I'm going to bring my assumption in. I know that 12 to the k is bigger than 7 to the k plus 5 to the k. So this line is bigger than 12 with 7 to the k plus 5 to the k. Do we understand that? So again, let's read that. 12k plus 1 equals 12k times 12. Yep. Now, this 12k is bigger than 7k plus 5k. So this 12k is not equal to, it's bigger than 12 7k plus 5k. Any questions? This line is equal to 12 7k plus 12 5k. Do we get that? This line is equal to this line, right? Because you can't say this line is bigger than this line. All you've done is expand. Now, what did you have on the right-hand side? On the right-hand side, isn't it actually 7k.7 plus 5k.5? So isn't 12 bigger than 7? And isn't 12 bigger than 5? So therefore, can't you now say that is bigger than 7k plus 1 plus 5k plus 1? Since, I don't know, you can say in two ways. You can say since 12 7k is bigger than 7 7k and 12 5k is bigger than 5 5k. You could even say since 12 is bigger than 7 and 5. Therefore, 12k plus 1 is bigger than 7k plus 1 plus 5k plus 1. Okay. was that? Ben, good recap?
Yeah, it is.
You remember it now?
Yeah, I've been practicing summation and divisibility, but not
Yeah.
as much with inequalities. Yeah,
Yeah, no, because there's no inequalities for
for
three.
three.
That's fine. That's fine. Let's do some more. Any questions from anyone? Go before I do another one. All right, let's try another one. And then step 4, hence true by mathematical induction, whatever. Step prove by induction. Let's do a factorial one. I think that'll be fun. All right, let's try this. All right, here we go. So, left-hand side. Sorry, what am I doing? Step 1. Step 1. All right, step 1 is test. It says all positive integers, so the first one is going to be test n equals to 1. Your left-hand side is equal to 2 times 1, which is 2, take away 1, 1 factorial. So left-hand side is 2, 1 minus 1, which equals to 1 factorial equals to 1. Your right-hand side equals equals to 1 factorial to the power of 1, which equals to 1. Therefore, left-hand side is bigger than or equal to right-hand side. Step 2, nice and easy step. Step 2 is going to be assume n equals k. So that becomes 1 factorial times 3 factorial times 5 factorial times 2k minus 1 factorial has to be bigger than or equal to k factorial to the power of k. This is going to be a bit interesting, I think. We'll keep trying. Step 2, step 3. Step 3, we've got to prove true for n equals k plus 1. So again, you guys know me, i.e. we're trying to prove 1 factorial times 3 factorial times 5 factorial times all the way up to k and one more term, right? K plus 1 term, so times, and then 2k plus 1 minus 1, 2k plus 1 minus 1 factorial has to be bigger than or equal to k plus 1 factorial to the power of k plus 1. I'll pause there. Any questions? Anyone not see what I've done in this line here? So n equals k plus 1 is everything up to n, up to k, sorry. That's what we say sum of k, and then one more term. The k plus 1th term, one extra term. Any questions? Okay, let's start. Left-hand side. Left-hand side is all of this times this, but what is all of this equal to? What is all of s of k? What is all of that? Well, isn't all of that just k factorial times k? So I'm just going to be a bit slower. So 1 factorial times 3 factorial times 2k minus 1 factorial, all of that, times 2k plus 2, 2k plus 2 minus 1, 2k plus 1 factorial. This bit here is greater than or equal to that, so this is bigger than or equal to k factorial to the power of k times 2k plus 1 factorial. I said it's going to be interesting. All right, any questions while I just play with this a little bit? K factorial, k plus 1, k plus 1. K plus 1. And if I try to pull it, would that help? Let's have a look. Minus k factorial k dot k factorial k plus 1 k plus 1. Factorize k factorial out 2k plus 1 factorial minus k factorial k plus 1 k plus 1. Don't like it. I don't like it. Let's have a look. Maybe I didn't do it that way, but it's 2k plus 1, 2k minus 1. You take out your 2's, that's going to be k terms, k factorial. So up to here would be k plus 1 to the k. Unfortunately, he's not a question that it's just a matter of saying, oh yeah, it's just going to become this, and therefore this bit is bigger. It's not really accurate. So you can see what's happened. It's right. It's just that it's not a really good question. There's probably better questions that actually make you test your understanding rather than you assuming and fudging it out. But here it is. So that's your k value, like we had, right? And then your k plus 1, and then you end up with that is greater than or equal to k factorial times 2 power of k times 2k plus 1 factorial. Then this obviously is still k factorial to the k. 2k plus 1 factorial can be written as 2k plus 1, 2k minus 1, all the way until you get to k, k plus 2, k plus 1, then k minus 1, and then all the way down to 1. Right, that's the logic of it. And then this component here everything extra that you're going to have, other than these two, so k plus 1 factorial, is automatically bigger than k plus 1 to the k. So this multiplication is going to be bigger than k plus 1 to the k. And the only reason why you would bring k plus 1 to the k in is because, as you can see on my right hand side, you can see I've got k plus 1 to the k. So it's more of a fudging technique. It's not really a justified way of doing questions. And then once you know that, you're just going to bring everything in and say, hey, therefore it's equal to the right hand side. So really poor question choice, but it is what it is. Fudging's part of the game, and there's a question. I just like having questions that work and work nicely. So unfortunately, he's just made it go, okay, that's that. Therefore, this bit here is going to be bigger than this, and you're done. So I'll show it again. That's your 2k plus 1 factorial. You'll stop at k plus 8k plus 1 factorial. You'll say that bit there is bigger than k plus 1 to the k, because that is obviously going to be a lot larger than this. And then it's just a matter of expanding. So what do we have? K plus 1 with k factorial, same powers, and then that becomes k plus 1 factorial to the k times k plus 1 factorial, and then bring it in together. And that's it. So literally just rewriting this step here that I've got backwards. But like I said, it's not really a very good way of doing it. So that's it, unfortunately. That's the question he's chosen. That's the question we just did. So just rewriting everything backwards. Oh well, very bad, but that's how it is. Let's do what else? Okay, so now there are also questions where you might have to use calculus or whatever the requirement is to prove the induction results. So let's say this one here, which was asked in the HSC, I think back in the 2009 Extension 1 paper. It was, I think, the last question. A lot of students struggled with it only because they've only used to, summation, divisibility, and inequality, and all of a sudden it's saying differentiate. They're like, wait, what? Because they know that's true, but to prove it by induction, some students got really stumped by that. But actually, really straightforward. So observe. Step 1, as always, test true for n equals to 1. So the derivative of x is equal to 1, and the derivative of x to the 1 is 1. Yep, that's right. The next one, right hand side. Right hand side is n, so 1 times x to the power of 1 minus 1. Anything to the power of 0 is 1. So therefore, left hand side equals right hand side. See how it just works out. Now step 2, you said assume true. So a lot of students got up to this stage with no dramas. D on dx, x to the k. So they were awarded 1 mark because it was a 3-mark question. There it is. And everyone failed, oh not everyone, a lot of the state actually failed to recognize how to do the last bit. Prove true for n equals k plus 1. So i.e., they're trying to prove that the derivative of x power k plus 1 is going to be k plus 1 x, x, and then to the power of k, which we know is true, because when you differentiate this, you bring the power down, and then take away 1 from the power. But you have to prove it. So what a lot of kids did, just wrote, okay, left-hand side's this, and then differentiate it, and it gives you right-hand side. That's great, but unfortunately, that's not really induction, is it? You just did calculus. Induction, you've got to always bring your assumption in. So if you've got to bring your assumption in, It's going to look something like this. X to the k dot x. Right? And the derivative of 2x's, how do we do this? How would you do a question like this? What am I trying to make you guys understand? The derivative of these 2x's, how are we going to do that? What must you use? Product rule. So then you're going to have u dash, which is the derivative of xk, which is our assumption, times v, plus v dash u. And then from that, you'll get k x to the k plus x to the k. You'll factorize your x to the k out. You're left with k plus 1. And I think that becomes the right-hand side. So you can use induction for a lot of things, as you just saw now. And they work really well. Got the product rule, yeah, pretty much the same thing. Now you can prove your binomial theorems, which we'll do it next term. Once we touch on binomial and binomial expansion and everything, I'll actually prove this. It's one of my questions we'll do. You can do in part of geometry. Oh, there we go. I want to do these ones. So the recursive ones. Okay. Now I don't think we did strong induction. Does anyone recall us doing strong induction? Like these type, where it says a sequence defined by b naught is this and bn is this. Prove that bn equals to that. Anyone? Have we done these ones before? These styles of induction questions?
You did an example of strong induction, but
just once, right?
Yeah, once.
And that's
yeah.
it. Yeah, I thought so. All good. So yeah, these strong induction types, let's have a look at them again. So the first thing you got to get clear is what you're trying to prove. Now, because there's two BNs, in this case, a lot of students get confused and they think, oh, that's the one you're going to prove or whatever. Clearly, it says prove BN is this. So your main term that you're trying to work out is this one right here. So normal procedure still, step 1, test true for n equals 1. You don't sub into this one, you sub into this. So you find b of 1, which equals to, I've got to tell them there's an error, 5 plus 4, which equals to 9. They had to give you that as well. We'll tell them to fix that up. So b1 is equal to 5 plus 4, which is 9. And that would already be given, and that's perfect. Okay? Then we have to do step 2. Step 2 would be assume true for n equals k, and then that becomes b to the k is equal to 5 plus 4k. Then we will do step 3. We're trying to prove true for n equals k plus 1. Now the problem is you're going to end up with writing this, right? So i.e. we're trying to prove bk plus 1 is equal to 5 plus 4k plus 4, which becomes 9 plus 4k. Now look, the problem is you can't break up this according to index laws. So you're never going to be able to bring your assumption in if you're not able to break this up. And that's when this guy comes in. So you have a relationship between Bn and one term before Bn. So b, k plus 1, left-hand side, is actually 4 plus b, and then k plus 1 minus 1 becomes k. But then what does bk equal to? Well, bk equals to 5 plus 4k. 5 plus 4k, and I think you guys can see that becomes 9 plus 4k, which equals to right-hand side, therefore true by mathematical induction. So these ones are actually easy, even though they're probably the most common ones that are tested. So they're not too hard, as long as you understand it the way I just explained it. So let's do another one. I reckon we've only done one of strange. No other ones. No. No. Fine. That's okay. Okay, no problem. No problem. I'm sure I can find one real quick actually. I'd rather do another strong induction before we finish up. That is pretty much it. That's even better. Okay. Okay. The sequence of numbers un is such that u1 equals 3, u2 equals 21, and un equals 7un minus 1 minus 10un minus 2 for n being greater than or equal to 3, right? Because you can't use this if n was 1, because then you'll get n minus 1, which is 0, and negative 2, which just doesn't work. Use the method of mathematical induction to show this. So that's what you're trying to show for n is greater or equal to 1. Don't let this confuse you. That's just making sure this stays positive. It's got nothing to do with you, right? They're trying to show this. So once you wrap that around your head, look how simple it is. So step 1, they gave you two things. You use the two things. So test n equals to 1 and n equals to 2. u1 equals 5, 1 minus 2, which equals to 3. True. u2 equals 5 squared minus 2 squared, 25 take away 4, 21, also true. Step 2, assume n equals k. So that becomes u to the k equals 5k minus 2k. And you're going to see we're going to have a problem, and you'll see how we're going to fix it. So right now, that's good. Just leave it as it is. Step 3. Prove true for n equals k plus 1. So essentially you're trying to prove u k plus 1 is equal to 5 k plus 1 minus 2 k plus 1, right? Again, uk plus 1, how are we going to bring our assumption in? Well, that goes into here. So that becomes 7 uk 7 UK minus 10 UK minus 1. Now, what's the problem? Well, I've got UK, that's done, but I actually don't have UK minus 1. So here, you have to also do n equals k minus 1, because you need an expression for UK minus 1, so you can substitute that in. And that's it. That's the strong induction bit. So I don't think it's too hard. Before I continue, does anyone have any questions? Pretty straightforward once you wrap your head around it. UK is 5k minus 2k minus 10. UK minus 1s, which are these lots. And then expand and hopefully get to this stage, right? We're trying to prove this right-hand side. So let me see what I would do. I would do 5k plus 1. Okay, I will do 7 5k minus 7 2k minus 10 5k on 5, because you know you need 5k, so you can actually simplify these, plus 10.2k on 2. Okay, 7 take away 2 is 5. Minus 7 plus 5 is minus 2. And I think we got it. So that's how your strong inductions work. That extra piece of information that's going to be given is just so that you can actually split up your UK plus 1 into your assumptions. I'm going to stop that recording there.